Well, let's see what we can get through then. Some of this is going to be repetitive since you learned it yesterday, but I do at least want to write it down. First thing that you should have learned yesterday is how to find the arc length of a vector valued function. Normally we use L. It's the integral from a to b of the square root of dx dt squared add dy dt squared add dz dt squared. It's the same as the integral from a to b of the norm of r prime of t. Okay, so like I said, we're going to set up an example, but we're probably not going to do all the integration because I think you guys can probably integrate it just fine. Example that we're going to do, we are going to find the arc length of the portion of the curve with parametric equations. X equals cosine of t, x equals 3 cosine of t, y equals 3 sine of t, and z equals 4t from the point 3, 0, 0 to negative 3, 0, and 4 pi. My first question for you, if I were to graph this curve, what would it be? Yeah, it's called a circular helix. So it's the one that goes like this up the z-axis. Okay, so our r of t is going to be that 3 cosine of t, 3 sine of t, and 4t. To find arc length, we're going to need r prime of t. So this will be negative 3 sine of t, 3 cosine of t, and 4. Arc length then. We'll figure out our bounds of integration in a minute. It's going to be the norm of r prime of t. So the square root of all those squared and added together, which would be 9 sine squared t, add 9 cosine squared t, add 16, integrating with respect to t. How do I find the bounds for t? Right, so look at your first point, maybe look at the z-coordinate. Z-coordinate is 4t. So 4t is equal to 0 when t is 0. And then I would suggest plugging in t equals 0 to x and y and make sure you get the same point. Over here, 4t is equal to 4 pi when t is pi. I'm assuming you can finish that. If you do, you end up with 5 pi. Okay. Sound good? Great. Okay. Did you guys get to the part in the book about arc length parameterizations? That's kind of confusing. Okay. So that's probably where we need to do a little bit more then. Okay, so a curve can be represented by more than one function. Okay, so for example, let's say we have some curve. I'm going to call it R1 of t, and it's described as t squared, and t cubed when t is between 1 and 2. That's one way of describing the curve. What I can do, though, is I can say maybe that t is equal to e to the u. So maybe I'm more interested in u than I am in t. Then R1 of u, so the same curve, but using u this time, t is replaced by e to the u. T squared then would be e to the 2u. T cubed then would be e to the 3u. When t is 1, that means u would be 0. When t is 2, that means u would be natural log of 2. Okay, so these two represent the same curve, they're just using different variables. So that's the idea with this section, is that t sometimes is not the best variable for us to use. Sometimes another variable might be more helpful. Now, if we found the arc length of both of these curves, using the formula from above that we did up here, you would end up with the same answer. Can you just trust me? I was gonna have us do both, but just trust me. Okay, so we're ready to move on then? Okay, so here's why this is helpful. The goal for today is we want to parameterize curve in terms of your arc length. Which we normally call S, rather than some arbitrary variable. Okay, so oftentimes t is arbitrary. It doesn't really have any meaning to us. S, though, does. S is arc length. So what we're going to do is we are going to write our curve in terms of S rather than t. Now, that doesn't mean that you can just replace t by S. That's not how it works. So we'll talk about how to do it and then look at an example and look at why we might be interested in that. Okay, so first thing, if we want our curve to be in terms of S rather than t, we need to know what the relationship between S and t are. So S of t, so S as a function of t, is going to be the integral from a to t of the norm of r prime of u du. That's the same as the integral from a to t of the square root of dx du squared plus dy du squared plus dz du squared, all integrated with respect to u. Now here's what this is saying. You are integrating, this should look familiar. This is the arc length function. So what you're going to do is you're going to take your function and you're going to use u rather than t. You're going to find the arc length. This time, though, you are integrating from some starting value to t. So t will stay there. That will give you a function of t. One thing that I want you to notice is if you take the derivative of s with respect to t, you're going to end up with the norm of r prime of t. Okay. Here's how you're going to use that. Example 2, we are going to find the arc length parameterization of the curve r of t is equal to cosine of ti plus sine of tj plus t times k with reference point 1, 0, 0 and the same orientation as the helix. Okay. So first thing we're going to have to do is we're going to find s of t, s as a function of t. We're going to need to integrate the norm of r prime of u. So the first thing that's helpful is to write r of u. So all you're doing is you're calling t and u the same thing. So that's going to be cosine of u, sine of u, u. We're then going to take the derivative. So we get negative sine of u, cosine of u, and 1. So s then, or s of t, we'll figure out the bounds in a minute. we're going to integrate the square root of the norm of this vector valued function. So we're going to get sine squared of u plus cosine squared of u plus 1, integrating with respect to u. Your bounds of integration, there's going to be a number down here. You're always integrating. Your upper limit will be t. This lower limit comes from your reference point. Your reference point is telling you where you're starting. So at this point, t is equal to 0, or u. Okay, so we're integrating from 0 to t. Sine squared plus cosine squared is 1, so 1 add 1 is 2 du. So this ends up being the square root of 2u from 0 to t. So we get our s of t to be equal to root 2t. Okay. So some of you are probably thinking, why do I even need this u? It's kind of useless if it's the same thing as t. Do you guys remember from calc how you're not allowed to have a variable here that's also you're integrating with respect to? That's the reason we have to use the u. You can't have t here and then also have it as a limit of integration. Okay, so the point here is in our original function, we want to replace t with s. So if we know that s is equal to root 2t, t then is s over root 2. So what I can do now is going back to that function, every t that I see, I'm going to replace with an s over root 2. So our r of s is going to be cosine. Instead of t, it'll be s over root 2 I, plus sine. Instead of t, it'll be s over root 2 j, and then plus s over root 2 k. Okay, so two things we need to talk about with this. First thing, with the original problem, I said you had to have the same orientation. So we have to, this function has to be going around the curve in the same orientation that the original one was. And I just kind of ignored that. Anytime you use this arc length formula, it's always going to be the same orientation. So anytime you go through this process, it'll be the same orientation. You don't have to worry about that. Other thing that we want to talk about is, why is this more helpful than the other one? So generally a follow-up question here would be, if we move along the curve, for 5 units, what are the final coordinates? So those units, that refers to s to the arc length. So if I look at whatever the arc length is, and I go along 5 times along the curve, where am I going to be? So what you can do then is you plug in 5 for s. So we would get cosine of 5 over root 2, sine of 5 over root 2, and then 5 over root 2. Just plugging into up there. That's about negative 0.923, negative 0.384, and 3.536. Okay. How do we feel about this? Do we see the use of this arc length parameterization? Okay, honestly, you're not going to use it outside of this section. There's not really, that I recall at least, other uses for this, in our context at least. Okay. Do we want to do another one of those? No? No, we're okay seeing it once? Okay. The other example I was going to do has u substitutions in it. Are you guys good with u substitutions? Okay. Great. Next thing then. we are going to let r of t be equal to natural log of t, comma 2t, comma t squared. We are going to find a few things. First thing that we are going to find is the norm of r prime of t. So using that function above, r prime of t would be 1 over t, comma 2, comma 2t. The norm then of r prime of t is going to be the square root of 1 over t squared plus 4t squared. One thing I want us to notice is this is 2t plus 1 over t, that quantity squared. So the norm then of r prime of t is just 2t plus 1 over t. Okay, quick note. Your book uses this notation. So when you see 1 bar, that's still the norm. I just tend to always put the 2 bars. So if this doesn't look familiar, it's because your book writes it differently. I want us to find ds dt. Now, if we remember s of t, what we wrote down is the integral from a to t of the norm of r prime of u du. So if I take the derivative with respect to t, I'm going to get r prime of t. What law or theorem is that? You did that last year. It is the fundamental theorem of calculus. Okay, so r prime of t, the norm, which is what we found above. So ds dt then is 2t plus 1 over t. Last thing, integral from 1 to 3 of the norm of r prime of t dt. Oh my gosh. Okay. This one I think you guys can find. Right? You're integrating that and then using the bounds from 1 to 3. Can we just skip it then? Yeah. Alex?
We had something like this on the test. Would you get points off for not simplifying the square root expression and you just left all of it?
If it's something that I think you should recognize, then I would take points off. In this case, if you left it like that, that's fine. I may, though, have you use it later, like here, in which case you would have to have it simplified. That make sense / answer your question? Okay, so we're ready to move on? Okay, is this helpful or is this just repetitive from what you guys did yesterday? Okay, next thing is curvature. Did we get to that? Okay, so pretty much starting at curvature, this is new, right? Okay, great. Okay, so next thing to talk about, like I said, is curvature. Some vocab, and this vocab is actually really important this next term. A parameterization is called smooth on some interval I if r prime of t is continuous and r prime of t does not equal 0 on I. So it can never equal 0 anywhere in the interval. Then we call a parameterization smooth. So we can either say a smooth curve or a smooth parameterization. It's the smooth that you think it is. Like there's no cusps, there's no sharp corners, things like that. That would be smooth. This is something that we're going to use a lot in the last chapter of Calc 3. If a curve is smooth, there's some shortcuts for what we're going to do in the last section. So for example, if we have r of t is cosine of t, comma sine of t, comma t, our r prime of t then is going to be negative sine of t, cosine of t, comma 1. Okay, so first thing that we need to notice is this is continuous. All three curves are continuous. Our interval in this case would make sense to be negative infinity to positive infinity. So always continuous. This will never equal the 0 vector. So I guess that should be the 0 vector. Hence, this curve is smooth. So it does not equal the 0 vector on negative infinity to infinity. And it's continuous on the same interval, telling us that the curve is smooth. Okay. With me so far? Okay. Here's why we care about that. Do you guys recall talking about big T? Did we look at that? Do you happen to remember what it's called? Yes, very good. Unit tangent vector. Okay, if you recall, the unit tangent vector was r prime of t divided by the norm of r prime of t. Reason we looked at the unit tangent vector is that it indicated the direction of the curve. So we're going to draw a picture so we can talk a little bit more about what that means. Let's say that you have some curve like that. If you pick a point, t is going to be something like that. It's going to be a vector that describes the direction. Few things to notice is right there at the peak, t is changing slowly. So if I pick the point that's right next to it, there's a little bit of change between the first unit tangent to the next one, but it's not much. Whereas something here, t is changing more quickly. Sorry, these are backwards. Here's where t is changing quickly. Here's where it's changing slowly. If I pick another one, they're going to be pretty similar. Does that make sense? I'm sorry, I just did it backwards. So do you guys see here that when we draw in the unit tangent vectors, they're going to be changing pretty quickly at the peak? But here, they're going to be changing much more slowly. Okay, this is the idea of curvature. Is we want to know at some point how rapidly is the curve changing. Okay, so that leads us to what curvature is, or how to calculate curvature. Okay, so if we want to know how rapidly t is changing, we're going to take the derivative of t with respect to s. Now, that would give us a vector, so we then want the norm. Okay, one thing to know is t has a constant length. It's a unit vector. So our curvature then is only affected by the change in direction. Okay. So here's an example of how you might see calculating curvature. Show that the curvature of a circle with a radius of A, show that that curvature is 1 over A. Okay, so ultimately the curvature is going to be the norm of dt ds. So we're going to need the unit tangent vector in terms of s so that we can take the derivative. We also know, as we wrote above, that the unit tangent vector is going to be r prime of t over the norm of r prime of t. So we're going to have to get our unit tangent vector, we're going to have to get it in terms of s, and then we're going to have to be able to take the derivative. So probably the best way to start is to figure out what r of t is. Okay. Anyone know the parametric representation of a circle? Close. Yes. So we have a cosine t, a sine of t. Okay, so what I'm going to do is I'm going to get the arc length parameterization first. So I'm going to get rid of t first. We're going to need r prime of t, which will be negative a sine of t and a cosine of t. We're going to find the arc length parameterization. So that's what we did earlier. We're going to start at 0 and integrate towards t. And then it will be the norm of this vector, remembering to use u. So it will be a squared sine squared of u plus a squared cosine squared of u du. Okay, you guys with me? Okay, so this then will be integrating from 0 to t. That'll end up being the square root of a squared, so which is just a du. So we end up then with s equals a times t. T then is s over a. Now, here's the thing we need to be careful of. We need r prime of s. We cannot go back here and plug in t. We have to go back to here. So you have to find r of s before you find r prime of s. So r of s then, taking this, substituting in for t, is going to be a cosine of s over a, comma a sine of s over a. Now, if we take the derivative, we're going to get negative sine of s over a, comma cosine of s over a. Okay, one thing for us to notice, what is the norm of this vector or vector function? 1. So if you can't see that, you could do the norm calculation. You're going to end up with 1. We ultimately want t of s, which is going to be r prime of s over the norm of r prime of s. Now, we already said the norm is 1, so our unit tangent vector will be negative sine of s over a. and then cosine of S over A. Okay, we're still chugging along trying to find curvature. Curvature is the norm when we take the unit tangent vector and differentiate with respect to S. So next thing we're going to have to do is take the derivative with respect to x. S, rather. Okay, so we get negative 1 over a cosine of S over a. And then negative 1 over a sine of S over a. Okay, we're good?
Yeah.
Okay, great. Last thing is we need to find the norm of this. So we end up with 1 over a squared cosine squared of S over a plus 1 over a squared sine squared of S over a. Hopefully you can see that that ends up being 1 over a, which we already knew is what we were going to get. Okay. Here's what I want us to see with this. If you have a circle with a large radius, that's going to give us small curvature. And that should make sense. If you take a really big circle and you move along the circle, curvature is going to be pretty small. The direction is changing not very rapidly. Does that make sense? Okay, what is the curvature of a straight line? 0. What object has a constant curvature? Circle. Yeah, circle has constant curvature. Okay, now, do you agree with me that this is a very tedious way to go about this? Now, luckily for you, there's a few other formulas. Okay, first one is the one that we just wrote down, the norm of dt ds. Okay, in my opinion, that is the most tedious and least helpful. These next two are a little bit more helpful. Other way, you can take the norm of t prime of t and divide it by the norm of r prime of t. Here's why you can do that. That numerator is really the norm of dt dt. Denominator is the norm of ds dt. We already talked about how these are equal. So you should see how that gets us back to the definition. And then the third one. Numerator is r prime of t crossed with r double prime of t, norm, all divided by the norm of r prime of t cubed. Okay, how we doing? Good? Okay, I am not gonna tell you specifically to use one of each of these. So I will never say, besides the next example, that you are forced to use one formula over another. You need to know them on a test. They might come up in a multiple choice question. Not multiple choice, true, false. So you do need to recognize them, but you can choose which one you think is the best formula. Sound good? Okay, are you guys ready to do one? Great, I'm ready for you to do one too. You are going to find the curvature for r of t is equal to 2t comma t squared comma negative 1/3 t cubed. Now, here's one I'm going to tell you. I want you to do this problem twice, once with formula 2 and once with formula 3. And you have until 9 o'clock. Good luck. I envision you maybe working with the person next to you. Yeah, they're over there. Can you check in with the person next to you and see if you are both on a similar track, please? How are we doing? Great. Have we got an answer yet using either formula? We have? Okay, I'm gonna let you keep working, but tell you that you should have gotten 2 divided by the quantity t squared plus 2 squared. So if you didn't get that, maybe check with the person next to you. For those of you who are ready, I'm going to start showing you what I did. Okay, my guess would be that you all had the right general idea, but that the functions were not the nicest. Okay, so did we have the general idea of how to go about this? So that's using formula 2. Did anyone get to formula 3? For those of you who used formula 3, I obviously got the same answer. In this case, I think that one was a little bit easier.
Can you go back up for a second?
I would love to. We done here? And go back up. Okay, this will obviously be in the video. I am not going to spend time tomorrow going over this problem again. So if you need to, watch the last 30 seconds of the video so that you can see this and go through what you need to go through. I know I threw a lot at us today. Was it horrible or not so horrible? It was medium. We'll see when you get to your homework.